cell, all right, what are the two reasons that people are putting them in? What's the reason, the two principal reasons that someone is choosing to install a stormwater control measure like a bioretention cell or a constructed stormwater wetland? Trust me, you say it, you're going to get it right. What's IIT Bombay say back there? What do you think? What are two reasons that... Okay, so they both deal with stormwater management. Water quality, it's one of them. What's the other one? Well, that does factor in for sure. That they're going to use the cost to figure out which practice to choose and exactly how to design it. Yeah. So water quality was one more thing we want to get that we worry about. And I'll give you a hint that the professor who spoke after me talked about this at length. Flooding. That's right. All right, so water quality and flooding. Now, for flooding, what did he say? And there's apparently, I don't know if it's codified into national design standards or if it was the suggestion. I didn't pick up which one it was. But from a flooding perspective, what type of storms would you be asked to design for in Roorkee? Roorkee would that be a class 1 city or not? Class 1 not, because it has one lock people. Did I say that right? And so this is not a one lock city. All right. So it's a secondary city. All right. Beautiful. I'm really happy we're here, but by numbers, it's not as big. So for most of the infrastructure for flooding, what was the storm that they want you to design to prevent flooding for? Storm that occurs once every how many years? You guys remember? 1 in 5 years would be for a major city. 1 and 2. That's exactly right. A 1 and 2 year storm. All right. Now, I am very confident that the Indian meteorological or climate data folks can tell you what the 2-year storm for Roorkee is. Imagine the meteorological office for the areas here on campus. In fact, we say in America, I'd bet dollars to donuts. You guys ever heard that term? It means I'm pretty sure it's going to happen. I bet dollars to donuts. All right. So that storm is what we use to figure out how much water we're going to pile up in a stormwater control measure. Whatever your 2-year return interval storm, that's how much we're going to pile up on top of our stormwater control measure. And we're not going to worry about that one today. What our exercise is going to be about today is determining what your water quality storm size needs to be. Okay? Because do you think it makes sense to make sure your stormwater control measure captures all and treats all of a 2-year storm? I see some no's. I think that's a correct answer. All right. Those of you are like, you're right. Why? Why? Why do you think it doesn't make sense to try to capture all of a... So I'm going to guess, and I don't know for here, but I'll guess that a 2-year return interval storm for Roorkee is probably between 100, I don't know the answer, between 100 and 120 millimeters of rain. Does anyone know? Does anyone know the website you can get to find out what the 2-year return interval storm is for Roorkee? In fact, do me a favor. Let's do that right now. You on your web. I'm going to do it on mine with my pocket computer up here. Find out for me, please, what the 2-year return interval storm is. You do that, and I'm going to do that right here and see. We'll have a race and see who can get it first. So what is the 2-year return period storm? 2-year A-R-I Rookie. See what we got. It's a 50% chance that occurs in a year, and it did not spit it out on my immediate. Let's see. Cannot imagine. So I didn't beat you to it, but it does come up and it says it's a 50-year storm. So I understand that. Annual maximum precipitation using frequency if it's in here.
It's over 165 mm.
How much?
165 for 2 years.
For 2 years. And what was the size of the event?
Something like this in 24 hours.
Yeah, that's what I got. 2-year return period. Is there what I'm looking for is an actual number. I know what the number is in Raleigh, and it's about 100 millimeters. 80, 90 to, what's that one?
109.
Great. Well, I bet I'm between 100 and 120. So it ends up being 109. Doesn't that make you feel good when you guess right? It makes me feel good. All right. So 109 millimeters. Thank you. Where did you get that number from?
I get it from the meteorological report.
Perfect. Perfect. Thank you. All right. So 109 millimeters is the 2-year storm, the storm that should occur, a daily rainfall that should occur on with a 50% average on a given year. Okay, 50% chance. So does it make sense to design a water quality volume based on a rain that will occur once every 2 years? How many of you say no? Right, no. And why is it that it doesn't make sense? There's 2 major factors. Economics. So basically, if you're designing to capture all the water and treat it, then the practice has to get a lot bigger, all right? And what's the second reason? It actually kind of deals with economics. The second reason is it's overkill. It's overkill. Because do you feel obligated, do you think the stormwater community feels obligated to treat 100% of the pollutant load or 98% of the pollutant load? No, we don't feel obligated. Anyone have a guess what the general consensus is? How much of the pollutant load should you choose to treat? Like how much pollutant do you think is a reasonable amount to try to treat? And just give me your gut, because I'll tell you what we use in America and what's used in Europe. But what do you think was a reasonable amount of pollutant load to treat? 50%? Yeah, people do it and use 50%. What's another number? Y'all tell me. 30%? Okay, by doing that, you're getting a lower number, a lower depth of rain, but that's a possibility. 30%, 50%, what's another number? 80%. 80%, you're getting quite close. And in fact, some jurisdictions would say 80% is fine. Most jurisdictions say 90%. That if they can expose, on average, 90% of the pollutant load to treatment, that they feel like they've done a good job. Is there something magical about that number? No. No. Maybe 80% is a good number, all right? Maybe it is. Maybe 80% is a good number. Maybe 90%. Maybe 70% makes sense, all right? But in the United States, especially on the East Coast, 90% is the magic number, but I'm perfectly good for it to be 80%. All right. Now, how many of you, by show of hands, know what the first flush effect is? How many of you ever heard of the first flush? Okay, well, now I'm going to go ahead and start drawing on this thing. I might need some help. Okay, which,
Use the laptop.
use the lot. I'm gonna have you help me out. Thank you. Just,
Right.
I'm just gonna write.
Give me 2 minutes.
No problem. I should have told you I was gonna write. So the first flush basically says that when it rains, do you think more pollutant load comes off initially? Or a little amount of pollutant load comes out initially when it starts to rain? A little? Okay. And I guess relative, it is just a little amount initially. But what the first flush says is that the earlier you are in the storm, the proportionally higher amount of pollutant load you get. All right? And that's due to this phenomenon called buildup wash off. Now, buildup is what the pollutants do over the course of a day or a week. Okay, that was great. That was great. Perfect. Thank you so much, Vinnarasi. It looks like it's ready for me to go now. So, oh, even better. Thank you so much. Woo! Oh, yeah. All right. And so what I'm going to do, it's not exactly right, but you're going to get it. We're going to call this the one-to-one line. All right. It's almost right, but it's not quite. That's the one-to-one line. So basically what this is percent of total pollutant all right, and this is percent of precipitation. All right, and so when we're at this point here, we'll go here. At this point here, we're going to go, that's 100% of the total precipitation. And over here would be 100% of the pollutant load, okay? And so what I'm going to want to draw on here now is what the first flush looks like. Yes? Oh, good. What I'm going to draw on here is what the first flush looks like. And I'm going to do it with, I'm going to see if I can change a color.
Color you can change it with the pen.
Hit that right here?
That you just.
All right, let's go blue. All right. If the exact amount of pollution that comes off, all right, this is my magic number right here. If the exact amount of pollution that comes off falls on this line, that means every millimeter of storm is delivering the exact same amount of pollutant, all right? That's not what happens, okay? What ends up happening is you have pollutants that are building up before the rain happens. The rain starts, and guess what? The initial part of the rain actually starts to wash off more of the pollutants. Now, what we would call a strong first flush, meaning the vast majority of the pollutants are early on in the storm, would look something like that's a very strong first flush. Now, I want everyone to take a look at that graph and see if it makes sense to you. All right, so the percent of pollutant, the total fraction of pollutant, is much higher in the early part of the storm. And then at the end of the storm, when there's not much pollutant left to wash off, okay, then there's hardly any more to add. All right, so this would be a strong first flush. All right. What do you think a weak first flush looks like? Does anyone want to guess? Anyone want to guess what a weak one? That's a strong one, where it's very early on, almost all the pollutant comes off. I'll show you what a weak one looks like. A weak one will go green. A weak one would do something more like this. Does that make sense? What does a weak first flush say? Is there still a first flush? First flush meaning that there's more pollutant at any given point, all right, then there has rain that's fallen. The fraction of pollutant is higher than the fraction of rain that has fallen. And so this is a first flush. This would be a weak one. Okay? Weak first flush. Anyone want to guess what a second flush looks like? What do you think the second flush does? What's that? I swore I heard somebody. Yeah, it's below the line. So I'll go with pink. A second flush will do something like this. That's a second flush. Okay. Different pollutants will tend to follow different ones of those. Strong first flush, weak first flush, or have a second first flush. How many of y'all think that solid sediment follows? If you had to pick for sediment, which one of those would you guess sediment has? A strong first flush, a weak first flush, or a second flush? Strong first flush. Sediment, oh, darn it.
Pink color.
Green.
You don't use some other color.
You don't, I'm going to go black. TSS, all right? Total suspended solids will either have a strong or weak first flush, all right? It does vary, but it's going to be somewhere up in this range. How about phosphorus? What do you guys know about phosphorus? Do people care about phosphorus here? What do you know about phosphorus? It's a nutrient, right? How does phosphorus get carried in the environment? It's a hitchhiker. 2/3 of phosphorus hitchhikes, 1/3 of it doesn't want to hitchhike. And by hitchhike, what does that mean the phosphorus is hitchhiking on? Sediment, that's right. 1/3 doesn't, 2/3 does. So phosphorus, if you know that, what would you guess phosphorus lines up here? Strong, weak, second flush, what would you go with? It'd probably be closer to weak, okay? It still has a first flush, all right? But it's closer to weak. But there's still a first flush, all right? How about metals? Things like copper. A fair amount of copper hitchhikes. A fair amount is dissolved, okay? The more of a pollutant that hitchhikes, the more apt it is to be a stronger first flush. So things like metals, cadmium, copper, they will tend to have a first flush, probably something more in the weak first flush range. Now let's talk about nitrogen. What do you guys know about nitrogen? Does it like to be dissolved, or does it like to be found in particulate form? It tends to be more dissolved. Okay? the more dissolved it is, guess what that means for the likelihood of a strong first flush? Is that higher or lower? How many, by show of hands, think nitrogen has a strong first flush? Okay. How many of you are like nitrogen has a weak first flush? Okay. How many of you are like nitrogen on average doesn't have any? Okay. Anyone here like nitrogen has a second flush? Okay. Nitrogen actually has sometimes a weak first flush. Sometimes nitrogen has a second flush. And then sometimes you can't tell. So nitrogen is the one pollutant that actually, I'm just going to be nitrogen. Nitrogen kind of does stuff like that. All right, nitrogen, But most of the pollutants you want, sediment, what do you think trash? Trash is a pretty, if trash is a pollutant, trash definitely has a first flush. Most of the trash is going to be washed off, unless it's a really big storm and needs big stuff. But basically, most of the pollutants have some first flush, and on average, it's weak. All right. Now, why is all this important? Because if you know that most pollutants that you're looking for have a first flush, that means that if you capture most of the storms, are you capturing on average more pollutant or less pollutant? Right, more pollutant. And so what we determined in the eastern part of the United States, and honestly, I feel confident this carries through across the board, is that if you want to get 90% of the pollutant load to be subjected to treatment, that's different from removing 90% of the pollutant. We'll worry about how much we remove later. But it's about how much of the pollutant load are you subjecting to treatment. Then do you need to get 90% of the rainfall if most of the pollutants have a first flush? You're right. Your gut's telling you no. You don't have to get 90% of the annual rainfall to get 90% of the pollutant load. You can get less. All right? And what has been sort of rule of thumb decided is that if you want 90% of the pollutant load, guess what amount of rain do they want you to capture on the long term for treatment? Take a guess. 80%. Okay? Now, it's a rule of thumb. And in stormwater, sometimes you just have to be really comfortable using rules of thumb. All right? Because honestly, every storm has a different pollutant load. Same pollutant, and if you were to graph this out, I'll just show you a bunch of TSSs. You'll see TSSs that do that, this, that. There's a couple that will do some of that, but most of them are but everyone's different. Everyone's different. So it is important to be comfortable with working with error on both sides in the world of stormwater. It actually makes structural engineers very uncomfortable. You know why? Because they like really knowing the number, right? They like having a defined, narrow range for numbers. Why? Because what are structural engineers designing? Buildings, bridges, and they really don't want that to fail. If we fail at sizing a water quality volume, you know what that means? It means we don't treat all 90% of the pollutant load. We treat 87%. And is that really a big deal? It's not that big of a deal, right? In the whole scheme of things. So we are okay with uncertainty, more so than a structural engineer. Structural engineers really care, and I'm glad they do. Next time you drive over a bridge, you'd be like, thank goodness the structural engineer doesn't care. I mean, cares so much about precision that we feel safe as we drive over the bridge. All right, so I'm going to, I think this is the erase button? Let's see. Nope. Oh, wait, yes. Woo! Oh my gosh. Oh my, what did, is this fun for you?
We'll save that.
What? Where's the eraser? My hand, right?
You want to erase?
I'm just gonna get rid of it. Oh, you have a highlighter? I can do like this.
You want to erase completely?
We'll just get rid of it. Oh, that. Vinnarasi to the rescue here. Okay.
Now you can use.
Okay, now I'm gonna try again. Okay.
Try once, whether it is writing.
Okay,
Touch this.
here we go. I wonder if that does it.
It's okay.
Okay. So we've established the first flush, and the first flush means that you can capture a lower amount of rain and still subject 90% of your pollutant load. So perhaps we capture 80% of rain to get access to 90% of the pollutant load. But honestly, it could be whatever number you feel comfortable with. It could be, you know what? I'm good with 70% of the pollutant load. And then maybe you only go with 50% of the rain. But we're going to go, for this exercise, we're going to go ahead and assume they want to capture roughly 90% of the pollutant load, which is associated with 80% of the rain. All right. So does that mean that we should look at 109 millimeters as the 2-year storm and say, let's just take 80% of that? It's simple, isn't it? But what does that say inside you? 90%, 80% of the 109 millimeter event. That's 80% of the 2-year storm. That's gotta give me 80% of the pollutant load, and it would, but it would actually give you more than 80% of the pollutant load. All right. Do you guys remember from the? Oh, we're back to red again, which is great. The professor that spoke after me had these charts, and he showed you the rainfall totals day by day by day. Uttarakhand was one of them. They had one for Kerala. They had one for Goa. Goa had some days of rain that were pushing 140 millimeters. Okay, but you remember we had all those. Well, what we want to know is on over. We don't want to capture 80% of the load for one big storm. We want to capture 80% of the load associated with a whole year or 10 years worth of record, right? We want to know what storms should we capture, should we design our stormwater control measure for, so that over the course of a year, we capture 80% of the pollutant load. So far, so good? Yep. All right. And so over the course of a year, you'll have, I'll put this in blue. Over the course, and I'm not going to pick a bunch of them, okay, blue. These are just different storm sizes, all right? And I know we have a lot more storms than this, but these are all individual storm sizes that have fallen, all right? And what we want to know, I'll put a couple of small ones in here too. Okay, we want to know, and okay, this is storm precip by day. And this is precip depth. So basically it's down here, it's just the day. This is the day. Okay, day and precip depth. Well, those types of records actually, it's nice to look at because you can see we had big storms and whatnot, but they're not entirely useful for us when the data are presented like that. Because that shows you what happened on a given day, and it shows you how much rain we got, but that is actually not terribly useful. But the data on that are extremely useful, all right? And so I'm going to hit this. I'm going to get rid of it. Boom. And I'm going to come back and hit this again. Let's go red. And what the data, if you resort the data, which is going to be the first thing I'm going to have you guys do with your rainfall record, okay? If you resort your data, what is super useful is if you can rank them from your smallest to over here, your largest. I know my lines are crappy, but you're going to have to deal with me, okay? From the smallest, all right, to the largest daily rainfalls, all right? And in the end, you're going to get actually a curve that's going to look like that, okay? So with your spreadsheet, can you do that? If you get your data, and they're all daily in millimeters, right? They're all daily rainfall depths in millimeters, and sort them from the smallest to the largest, or the largest to the smallest, doesn't matter to me. All right, so you want to sort them from the smallest to the largest so that you would be able to create a graph that looks like rainfall, depth, and this would actually be count, all right, with the lowest storms being at one end and the largest storms being at the other, okay? So rainfall depth, you want to basically rank the storm size all in millimeters. All right, now that, once you do that, then we are able to start determining what the 80 percentile storm is, okay? So is everyone clear about what you can do with your data to be able to rank those storms from smallest to largest? Okay, and when you're done, I'd like for you to please create that graph for yourself and for all of us. All right? So I'm going to let you guys do that. So you're going to create a rainfall depth, smallest to largest graph. And then when you get that done, let me know. Okay? And you guys can.
Excel file, rainfall data. What is the name of that file? Rookie daily data. Okay. So it is an Excel file only. In the Excel itself, you can create the graph.
Okay.
Just in the ascending order.
Okay.
Ascending order, and then create the graph.
So task number 1, create this graph. What's that?
Frequency diagram or just a depth only?
What's that?
Is it a frequency diagram or just the depth?
It's just and then what we're going to do.
It is actually a histogram they have to create.
Oh yeah, you're getting there. That looks good. A lot of really small stuff down in here that doesn't even register. Right. That's excellent. Oh yeah, that's good. And these are all and I guess there's a lot of just zeros on here the days it doesn't rain too, right? And that's fine. That's fine. You guys, this is great. So keep that. That's perfect. All right. As you guys end up getting your graphs, let me know. We got a couple right here that it look like they're spot on. Oh yeah, that's good. That's good. They're going to have a lot of zero because those are all the days they don't have any rain. But that's really good. Perfect. Oh, that's perfect. Oh, yeah, great. You're getting there, but that's exactly what we're looking for. All right, excellent. Great. That looks good. You have a question?
The data will be there in my system also.
I think we could do it too. Yeah. Woo. Okay. Ah. I need to, whoops. I'll just go to the desktop.
Here.
No.
They are bringing the data. Data is not stable.
Okay, no problem. So these guys are getting it. They're getting that.
We already saved here.
They've got it. They're good. Thank you so much. All right. Thank you so much. Sorry. Oh my gosh. So Nikhil, is this on IT Rookie? Gian?
Yes, sir. The top one
The
first.
top one. That makes sense. Gian. Rain Rookie Daily. Okay, great. Oh my gosh, you have all the way back to 1901. Well, that sounds. Say again.
Can you share it over screen and?
Oh, yeah, I will. Here, I'll let you do it.
ओपन बोर्ड क्लोज करना है.
Open with you can close it.
Close the open. Yeah. Yes.
Okay.
Thank you.
All right, great.
Yes.
Thank you. Oh, let's do it. Oh, wait, what the hell am I doing? Get this sword. 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 No, I need to get the whole thing.
Can do it. Okay.
I just want to get, all I want to do is get from E45291 to A. I was doing the long way, but I figured there's got to be a quicker way. Cancel.
Just okay, it will be there.
I'll hit OK, but I did not get the entire rainfall record. Smallest to largest is fine. All right. I did not get the entire rainfall record, but I do have it. All right. I've done that. Where's my graphs? Graphs. Mm-mm. Can you help me graph? I'm trying to get the graph. Yeah, that if I could talk you through it, that'd be great. That sounds great. So if you could just graph that out for me, that'd be super. Oh, I did not get all the way to the top, but for the purpose of the exercise, it's fine. All right. That's perfect. Yeah. Yeah, that's good. Yeah, that's perfect. Okay, great. Oh, yeah, it's great. Okay, great. Thank you. All right. So is that what everyone got? A graph looks like this? Yes. Okay, great. And so this is the this is the rank. All right. This is storm rank. If you could fit a curve to this with an equation, and that is actually totally doable. All right. If you fit a curve to that equation, then we would use that integration we do the equation for some integration, but I'll talk about it in a second. All right. So now that you've gotten all of your storms, and Vinnarasi, thank you for doing that for me. That was about 10 million times more efficient than I was going to be. All right. Now that you've gotten this graph all set up and your data all set up, then let's try to figure out how do we use this to determine what the 80% storm is, right? There's two ways that are commonly used across the stormwater management world. One is the simpler one, and to be honest, I'm not as much of a fan of it, okay? But the simpler one is to take a look at the storm counts and just pick whatever number in here is the 80th percentile. So literally, if this is 0 and 1 down here and 100 right here, people will pick the 80 number right there. All right. And so if you take a look at the number of storms, roughly how many days have rainfall in your record? How many days have rainfall in your record? There was what, 45,000 total days in your record, so there's a lot. How many? Speak up real loud for me. There were, I think, 291 days have rainfall in your record. Huh. Okay. So if there's 291 days that have rainfall, 0.8 times 291, 4/5 of that is going to be something around what, day 220? So from the ranking, so everyone had 291 days of rain, correct? Okay. Then take a look at the rainfall total in your ranking on roughly the 220th day, but let me do it real quick. $233rd day. So if you were to rank, I am surprised there's only 291 days of rain now over the course of it. Oh, that sounds better. There were 45,291 total days, okay? But most of them didn't have any rain. What's that? 11,000. Okay, thank you. 11,480. 11,480. 411. Oh, I see what you're saying. Okay. 11,411 times 0.8 is your 9129 day. All right. So if you were looked up the of the 11,000 days that had rain, and you look up in that ranking that you just produced, which you saw up there in a second, the number you had on your 9,129th day, that would be that means 80% of the rainfall events were that size or less. Okay? So what's that number? You guys can look it up. Let's take a little bit of time. So you're going to look up your 9,129th day. So that would be that means 80% of the days that had rain would have had that amount or less. But what was the maximum amount of rain they had? 240? 250? It's a big storm for a day. That's a lot. Oh yeah, a little bit under. Okay. To find out what the 9129 rank is. What's that? 70. 70. Okay. 7. 17. So you guys probably figured out I don't hear great. And I apologize. So if I say, what's that? I'm just trying hard. All right. That's actually a very interesting number because one of the common numbers that is used is what number that 17 would get maybe rounded up to? 20. Because that's just a nice number. People like using 20. So that is one way to do it. Now, it is simple, and maybe that's why it's done. But what do you think? What is potentially a problem with that simple method? What's a problem with it? The storms that are bigger than 17 millimeters, some of them are a lot bigger, right? A whole lot bigger, right? And so the other way that is used to determine what your first flush is actually trying to figure out. Can you go back to that graph, please? Thank you. Actually is there a way I can draw on this with my finger? Can I do both?
Whenever you want to draw something,
Just hit something over here?
just here, if you do like this,
Oh, that's nice.
then you can.
Perfect. Thank you. Okay.
You can take this pen.
I'm going to move it away. All right. Oh, can you do me a favor?
Sure.
Can you blow up from here over? Can you blow up basically that box? The zoom. That'd be great. By the way, that's great that you got 17. That's a nice number from which to start. And it may be the number that we pick. All right. I don't know. You might even be able just to zoom from here, Vinnarasi, and just make it bigger here. Oh, that's great. Perfect.
Sorry,
This is great. Thank you, Vinnarasi. That's great. That's great. All right. All right, so here is a blown up ranking of an understanding that there's a bunch that go up there. Everyone just understands there's a few storms up there. But if you're truly trying to get 80% of all the rain that falls, does that mean that we should completely neglect these storms? You're right. It's not fair to neglect them. Their feelings are going to get hurt. Moreover, they probably have a little extra pollutant load being how big they are, all right? So it's not fair to neglect them. And so the other way to try to figure out what your first flush is, or your water quality storm, is, let's see if this will work. Remember we said 80%. Okay, hold on. I'm going to do what you did before. This is not that good. What's that? In this? Oh yeah, there it is. There it is. There it is. Perfect. Is to figure out what value you get, all right, that if you integrated below this, you would get 80% of all rainfall. And if you integrated, therefore, everything above that line would be 20% of the rainfall. Does that make sense? If you integrated below this line, all right, whatever that line happens to be, and you got all these little tiny sums down here, you would have 80% of all the rain that falls. Now, why does it make sense? Well, if you build a stormwater control measure, do you think once it hits, say, 17 millimeters, it's like, okay, I'm not going to take any more water, all right? Or once, let's say, a 25 millimeter rain falls, does the stormwater control measure like, no, I'm not treating any of you? No, that's not true, right? Even if you design it for and you get a rainfall of 25, that stormwater control measure is going to treat the first 17 and then let the next 8 flow past, all right? So by integrating below this line, all right, you're not just getting the entirety of all the storms up to this point right here, all right? I'll make it black. Until this point right here, you're getting you're treating 100% of all of those storms, but then you're also treating some fraction of all these storms that exceed whatever this limit. We don't know if it's going to be 17, but I'll put 17 millimeters with a question mark, okay? So now the next thing I'd like for y'all to do is set up a simple model, all right, where what we do is I literally just try a number of millimeters, all right, and to determine when I hit my 80% of rainfall value, all right? So let's say you pick 17 millimeters. What you would do is you would subtract 17 millimeters from every storm that exceeded, okay, and then kick those values into some pool where, and then you would add those all together, and then you'd see how that value compared to all of this that you had then add. So it is a cumulative determination. Does everyone understand what I'm trying to get at here? It's a cumulative determination. So you're going to get up to a certain size storm, you're going to get all of it, all right? And you might try 17 millimeters since that was the 80 percentile event doing the old way, the simpler way. Okay, and then everything beyond 17 millimeters, you subtract, and it's great that you subtract 17 from it, and then whatever the difference is, if it's 18, it's only 1 millimeter. If it's 240 millimeters, then you're actually kicking over 223 to this other set. So you want 20% of your volume to be associated with this, and 80% of your volume to be associated below the line. Does everyone understand where I'm trying to get at? Do you think you can go ahead and give that a shot? it's just a relatively quick, you have to calculate it out, but it's a relatively simple formula, all right? And all you're doing is you're comparing the total values here to the total value in that. All right? Why don't you guys have at it and see if you can get it? And I'm going to go to the restroom. Okay, great. I'm sure it's up here.